Okay, goodness of fit. Goodness of fit is a good way to check to see if a bunch of different categories are doing what we expect. In other words, like for this example, we roll a die and we roll it over and over and count up how many times 1, 2, 3, 4, 5, 6 is shown, and then we look at the results. Now, if you know anything about dice rolls, you should be getting approximately the same number for each side. And so if you look at this, you might be thinking, well, what about this 15? Or this 5 and the count of 14? That seems like it's really high. And so we might say that, hey, this must be a loaded die because I'm getting 5 way more than the others. But you got to realize that it may not actually be significant. This may just happen by random fluke. So we got to be able to test for the difference. And that's where goodness of fit comes in. So you open up GeoGebra. You go to probability calculator. And then you go over to statistics and you gotta select the goodness of fit test. Now we have 6 categories, so we're gonna put 6 rows here. 1, 2, 3. Alright, and then we gotta transfer our observed counts here. And so, I'm gonna try to fit this all in one screen here. Alright, we would copy in the counts. As I'm doing this, you gotta be really careful here because you cannot put percentages. If you put percentages, you're going to get the wrong kind of results. You'll get a result, but it's going to be wrong. They need to be actual counts. So like if you were in, say, League of Legends and you're looking at the win percentage of different heroes and you wanted to know if they're all approximately balanced, they're all about the same percent, then you would have to actually look up how many times they won, not the percentage of wins. So here we have the times that we rolled this die, and then the expected count is really important. Like if you had a balanced game, you would expect all of your heroes to win about the same percent of the time. And if you have a balanced die, you should be expecting all the numbers about the same amount of times. And so if we have 48 rolls, 1/6 of those rolls should be 1, so that would be 8. And actually for all of these, they should all be the same, so we expect 8 all the way down. Alright, and so when it does the goodness of fit test, it gives you a p-value. We got 0.1195. And our confidence here is at a 95% level, so our alpha is 0.05. This yet again tells us that we can't conclude anything fishy is going on. This actually could happen, quite possibly with a normal die, just with random variations. And so we would say there is no weight to this die. We can't conclude anything. If we got below 0.05, then we could say, wait a second, I think this die, there is something going on here because it is extremely unlikely that this could have happened by random chance. And so we would have rejected the idea that it is a balanced die. So the same thing could happen with like win rates between, for example, in StarCraft. If you have a win rate between the 3 races, you have Protoss, Zerg, and Terran, and you put in the counts here, let's just do an offhand example. So Protoss, Zerg, and Terran. If you observe Protoss in a tournament winning that much, and Zerg winning that much, and then Terran winning that much, now that's what we would do for an expected count is we would take the total and divide by 3. Because in a game that's balanced, we should be expecting about the same amount for every race. So it would be about 25.6 for each of these. So I'm just making this up. Okay, but in this example, if we observe these number of wins and we see the expected over here, in this case, even though it's pretty off for Zerg, we can see that, statistically this might happen quite easily. It's way above our level. And so this is a great way for you to test balance of games. Just please remember, don't do percentages.